Yeah, welcome back to our second half. Let me introduce Freddie Illingworth, who will be talking to us about minimal degree stability and locally colourable graphs.
Thanks so much. Thanks so much to the organisers for organising this, and Carla for inviting all of us Epsilons to give these talks. Please interrupt me at any moment if you have a question or it doesn't make sense or I'm speaking too quickly or anything. So I'll be talking about two things which I think are sort of similar but not obviously closely related. So one of them is going to be minimum degree stability, which I'll mostly focus on, and then I'll chat a bit about locally colourable graphs later. So the setup for minimum degree stability is like classical edge stability results from the sort of 60s. So throughout, we're going to have some graph H that we're going to forbid, and it's going to have chromatic number r plus 1 just to make all the expressions nice. And so G is going to be some generic H-free graph on n vertices where n is really large. And so if H is if H is a clique or something, then we Turan's theorem tells us most edges G can have, and more generally, Ehrlich and Shimonovich proved upper bounds for the number of edges G can have, which is this third bullet point. So G can have at most essentially 1 minus 1 over R n choose 2 edges, and you can see this is attainable by taking a complete balanced R-partite Turan graph on n vertices, and that won't contain H because it only has chromatic number R. But the result we're more interested in is this red bullet point, the fourth one, which is an edge stability result. So if a graph has that many edges, then it's close to being R-partite. So if you're H-free and you have close to 1 minus 1 over R and 2 edges, you're close to R-partite. And for this talk, close to is going to mean that you can delete little of n squared edges to make it R-partite. So you can delete sort of 0 proportion of the edges to make it R-partite. And if I ever say something's far from something, I mean you can't delete little of n squared edges. You need to delete at least constant n squared edges. So just a sort of simple example, if H is the 5 cycle, so R is 2, then the most edges 5 cycle free graph can have is sort of a half n choose 2, and what they look like complete bipartites, these two blobs, lots of edges between, and essentially no edges inside, sort of smattering of edges inside. So I just want to quickly note that you couldn't get rid of this ability to delete some of the edges. So for general H, there are examples of H-free graphs with 1 minus 1 over R n choose 2 edges that aren't R-partite. And in fact, there are some where you can make the chromatic number really quite high. And you do this by sort of putting some graph of high chromatic number inside one of the blobs, inside one of your parts. So we do need an approximate sort of stability. We do need to be able to delete some edges. And I think a natural question at this point is what happens if you go below 1 minus 1 over R? So you've got some H-free graph. What if it has constant n choose 2 edges where the constant's a bit below 1 minus 1 over R? Is it close to, maybe it's not close to R-partite, but maybe it's close to 2 R-partite or something else? And sadly, that's not true, and it's really not true. So if you go a bit below 1 minus 1 over R and choose 2 edges, then the chromatic number can be large and it can be far from being small, but for a slightly silly reason. So how do you do this? What you do is you take some big, nice, complete R-partite graph on lots of the vertices, and then you squirrel away some high chromatic number on a small proportion of the vertices. So here's a particular example, 5 cycle, again R is 2, and we've gone a bit below a half n choose 2, we've got down to 0.49 n choose 2, say. So we've got some big, complete bipartite graph on 99% of the vertices, and we've got this other bad graph here. And I think we had mentions of blow-ups in previous talks, but I'll just define it again. So I've got a particular example of a bad graph. So this is a 7 cycle, and we've blown it up. So that means all the vertices have been replaced with independent sets, and if there was an edge, it's replaced with a complete bipartite graph. So this is a load of blobs, all the edges between adjacent blobs. And this thing doesn't have a 5 cycle, isn't bipartite, and it's far from being bipartite, because to make it bipartite, you essentially need to delete all edges in consecutive parts, which is sort of constant n-squared edges, a small constant, but still constant n-squared edges. So we've used the left-hand side of the graph to make the edge count high, and this small right-hand side to make the chromatic number really large. If we wanted to make it far from 100 partite, rather than using a 7-cycle, we'd use some other bad graph and blow it up, which is kind of a shame. So, but it feels like a silly reason for not being close to R partite. We've managed to squirrel away this high chromatic number on some tiny proportion of vertices. How do we sort of stop that happening? Well, quite a common thing that you can do, and that's if anyone went to Yuval Wittgenstein's nice talk yesterday, you can ask rather than asking for many edges, why don't we ask for a high minimum degree? So we're looking at HB graphs with high minimum degree, and again we're going to look for the same conclusion as the Shimonovich edge stability. We're going to say we want to be able to make it R-partite by deleting few edges. And so this is what this definition here, this graph parameter delta H is meant to encode. So what's the smallest constant where minimum degree at least constant n, and being H3 implies being G is close to R-partite. So for edge stability, we said there was stability at 1 minus 1 over R, nothing below, that wasn't below, that's sort of all you have. Here we're going to see it's a bit more nuanced. It doesn't just depend on the chromatic number, it depends on other structural properties of H. So yeah, let's start with a nice example. So if H is a triangle, so R is 2, any triangle-free graph has at most a half n choose 2 edges. So any triangle-free graph has minimum degree at most a half n. And now let's imagine dropping this minimum degree slowly, but maintaining triangle freeness and asking, what does the graph look like? What does G look like? And actually, if you drop a half n down to 0.45 n or even further, the graph has to remain bipartite for quite a long time. And then suddenly, there's like a phase transition. Does anyone have an intuition for where there might be a phase transition where suddenly you go from being close to bipartite to far from bipartite?
Maybe C5 is.
Yeah, exactly. So at 2/5, suddenly the 5-cycle appears. So until 2/5, it remains bipartite, and we'll see reasons why in a later argument. And suddenly at 2/5, you can have triangle-free graphs which aren't close to bipartite, then more like 3-partite, which is this blow up of a 5-cycle. So I've written K3 is not homomorphic to C5. If you know what a graph homomorphism is, that's great. If you don't, you can just think of being homomorphic to as meaning being a subgraph of a blow up. So when I say K3 is not homomorphic to C5, I'm just saying this blow up of the 5-cycle doesn't contain any triangles. And so this, well, provided you believe me that it remains bipartite until we get down to here, this shows that delta K3 is 2/5. So if the triangles is 2/5. And this is a special case of a result of Andrzej Erdős and Schoch from the early 70s. And they effectively gave delta H for any clique. And 5 cycles what you want, but you just take a 5-cycle and you join it to a sufficiently large clique. In some sense, I think one of the ideas I get across is that in something the graphs are what matter. Like the numbers just follow from the graphs. Once you've sort of working out what graphs you think are the ones where the threshold changes, and then it's like a lot of the work. Because once you've worked out what the graph is, like at least you can start the proof. If you don't know what graphs you're aiming for, it actually becomes almost impossible to guess what the answer should be. Great. So. Yeah, what about for sort of general H? Not very much was done for sort of any other H. So I'll first discuss what happens for 3 chromatic H, just because that's a particularly clean result, and it will suggest what might happen more generally. So H is some 3 chromatic graph, and we've seen that 5 cycles are obviously interesting, and it's not surprising that possibly other odd cycles are going to be interesting. So if you've got your H and you look at the odd cycles and you see which is the first one it doesn't appear as a subgraph of its blow up. So what's the first one it's not homomorphic to? So for the triangle, that was just C5, right? Triangle is not a subgraph of a blow up of 5-cycle. So that was the first graph. But if we take an H to be a 5 cycle in the previous example, this big blow up of a 5 cycle wouldn't have appeared because the 5 cycle is a subgroup of that, so it's not C5 free. So if you start with a C5 free graph and minimum degree is at most half n, if you lower that minimum degree, the thing remains close to bipartite until you get to 2/7. And then suddenly the 7 cycle appears. Right? So a blow up of 7 cycle, free colorable, not close to bipartite, doesn't contain a 5 cycle. And so that's how this sort of gives us what delta H is. So you might wonder, I've said that there definitely is a smallest positive integer where H won't be homomorphic to the odd cycle. That's true just because H is not bipartite. So suppose it has some odd cycle, let's say it has an 11 cycle. H won't appear as a subgraph of a blow up of a 13 cycle because the blow up of a 13 cycle doesn't have any 11 cycles in it at all. So there will be a first G to which H is not homomorphic, and then that immediately gives you delta H. So I think we see why delta H definitely has to be at least 2/2G plus 1, right? Because the blow up of this 2G plus 1 cycle doesn't contain H and is far from bipartite. So you need at least that minimum degree to guarantee being close to bipartite. But a good question is sort of why doesn't it happen earlier? Why are the odd cycles the only interesting graphs that we have to compare things to? So let's, just see. This is sort of like a shortish proof, or sort of sketch proof of what's going on in this case, and some of the ideas like are also used in the more general case. So we're looking at delta C5. So we've got some n vertex graph. It's got no 5 cycle, and we want to say if its minimum degree is much bigger than 2/7, or away from 2/7, then it's close to bipartite, because that would show us that delta C5 is 2/7. So pick any odd cycle in G of length at least 7. So sort of long cycle in G. And now let's count the edges between the cycle and the rest of the graph. Well, from C's perspective, each vertex of C sends delta, like minimum degree of G edges, the rest of the graph. So the number of edges between C of G is at least size of C times the minimum degree, and that's at least sort of 2 plus 7 epsilon times n, because C was a cycle of length at least 7. From G's perspective, that's saying the average vertex in the graph has 2 plus 7 epsilon neighbors in C. And in particular, lots of vertices in the graph will have at least 3 neighbors in C. And so here's like a vertex V, and it's got 3 neighbors in C. So 1, 2, 3. And you can check if you've got an odd cycle and some vertex has 3 neighbors in that odd cycle, you get a shorter odd cycle. So here is sort of the black, or the original cycle C had 9 vertices, and now this new cycle with V has 7 vertices, and we can then play the same game on this new shorter odd cycle. And so if we sort of play this game, then what we see is that any long odd cycle, so any odd cycle of length at least 7, produces a short odd cycle. So this sort of sketch, this idea suggests that if there are lots of odd cycles in G, then there are lots of triangles, or there are lots of short cycles in G, so lots of triangles or lots of 5 cycles. And by lots, I mean sort of there are constant n cubed triangles or constant n to the 5 cycles. And it's kind of a sort of slightly, standardish extreme graph theory thing that if you've got lots of triangles in a graph, there'll be a large blow up of the triangle. Or if there are lots of 5 cycles in a graph, there'll be a large blow up of the 5 cycle. But blow ups of triangles contain C5s. Obviously, blow ups of C5s contain C5s. So if there are lots of odd cycles in your graph, then G contains a 5 cycle. Which that's a contradiction. So actually, G must have few odd cycles. If G hasn't got many odd cycles, then one would hope, and indeed the sort of graph removal lemma suggests that you could delete few edges from G to remove all these odd cycles. So you could delete little o of n squared edges from G to remove all the odd cycles. So G should be close to being bipartite. So this essentially establishes what we wanted, that above 2/7, your 5 cycle free graph is close to being bipartite. Great. Okay. So what about for sort of more for H with higher chromatic numbers? We've seen that odd cycles sort of play the key role. You just compare your graph to odd cycles, and that tells you what minimum degree stability it has. And hopefully, hopefully there'll be some sort of sequence of graphs or something like that. And well, we don't know if there is sort of infinite sequence, but the slightly strange result shows that there certainly is a start of a sequence. So we're given some graph H with chromatic number bigger than 3, and you want to determine delta H. You compare it to a sequence of 11 like explicit graphs. Check, is it a subgraph of each of their blowups? And the first one is not a subgraph of. It's great, immediately tells you what delta H is exactly. Sadly, H could be homomorphic to all of them, possibly, which would be quite strange. There aren't sort of any H one commonly thinks about won't be homomorphic to all 11 of these things. I'll show you what they are in a second. But if it is, then we at least have bounds on what the minimum degree stability of H is. So we've sort of pushed it down. And just to give you numbers, just to sort of fix in your mind, Turan's theorem says minimum degree is at most 1 minus 1 over R. So in some sense, we've got 6/7 of the way down to just 1 minus 1 over R minus 1. So we're sort of 6/7 of the way of determining delta H, although the last 7th will be kind of harder than the first 6/7, one imagines. So what do these graphs look like, these FG that you're meant to compare things to? We're given odd cycles with super importance for 3 chromatic. One would imagine that if we asked what's an obstruction to being close to 3-partite, you expect odd cycles joined to a vertex to be there, sort of intuitively, so sort of odd wheels. And that's true. So 6 of these cycles are odd wheels. And for higher R, you just take a clique joined to an odd wheel. And the other 5 are these slightly strange looking graphs, which possibly, well, certainly the right 4 possibly don't see in your life. The one on the left is the complement of the 7 cycle, or alternatively the square of the 7 cycle. But so what are these doing? Why are these here? Well, odd wheels deal with the case where you have lots of vertices whose neighborhoods contains an odd cycle. So the other obstructions to being close to 3 colourable shouldn't have aren't going to have those in. So they're going to be graphs where every vertex's neighbor is bipartite, doesn't contain an odd wheel. So all these 5 graphs, you can check that if I take a vertex and look at its neighborhoods, it's bipartite. So for example, in the complement of the 7 cycle, each vertex's neighborhood is a path of length 3. So it's bipartite. And so if we want to understand minimum degree stability, essentially we've actually got a new problem, which is we need to understand graphs where every neighborhood is bipartite and have large minimum degree. That's our sort of new game. And that now we can sort of see the sort of locally colourable idea comes in. If anyone has any questions on minimum degree stability, now is a pretty good time to ask. So I'm going to segue to locally colourable graphs. Okay, cool. So let's start with just locally bipartite graphs. So every neighborhood is bipartite, and we want to understand their chromatic number and their structure. And this is quite natural, even obviously it's nice because if we understand these properly, we just determined that minimum degree stability, which is pretty natural. But also, it's quite a natural question because we're saying a graph every neighborhood has low chromatic number. Every neighborhood is large because it's got large minimum degree. So you'd expect that the whole graph should have quite a small chromatic number. And this is a variant of being triangle-free, right? So triangle-free graph, every neighborhood is independent. So every neighborhood is 1 colourable. So likely bipartite saying, well, every neighborhood is 2 colourable. So more generally, you can think about locally tripartite or whatever. And actually, it's sort of a variant of triangle-free, but it also this family of graphs lies between triangle-free and K4-free. because a K4 is like a vertex joined to a triangle, so it's not locally bipartite. So quite a natural harmony graphs squished between these two. And if we're going to determine delta H, we need to understand the structure of these, where the minimum degree is between 1/2 and 2/3. And our results, well, my results are down to 8/15, that's the same as the 7th gap. So if you can get 8/15 down to 1/2, then dreamy, you've got minimum degree stability sorted. I just want a quick word about what we mean by these sort of homomorphism and subgraph structures. So at the bottom, I've drawn these graphs, and this is for triangle-free graphs with large minimum degree. We know minimum degree bigger than 2/5 means bipartite, which is the same as saying it's a homomorphic to an edge, right? It appears as a subgraph of a blow-up of an edge, because a blow-up of an edge is a complete bipartite graph. And then below 2/5, well, at 2/5, suddenly the 5-cycle appears. And if you go a bit below 2/5, you know every triangle-free graph with that minimum degree is homomorphic to a 5-cycle, so it's a subgraph of a blow-up of a 5-cycle. If you go a bit further down, you get to 3/8, then suddenly a new graph appears, this sort of Mobius ladder thing, which is 8-cycle with edges across. And for triangle-free graphs, this over 30 years, this has been determined fully. So sort of what these graphs are and what, as you drop minimum degree, what you know about the structure of your triangle-free graph. So we're looking for those sorts of things. Great. So at the top, this is just a reference. This is what happened for triangle-free graphs. So the 2/5 stuff was on justification in like 70s, and then Packers stuff in the 80s, Gin in the 90s, and Brandon Thomas in the early noughties. So what they showed was, if you want a triangle-free graph to be bipartite, you need to know its minimum degrees in these 2/5. 3 colourable is sort of slightly weird fraction, 10/29, it's a bit bigger than a third. And then if its minimum degree is bigger than a third, you know it's 4 colourable. And if you drop below a third, suddenly there's like a huge phase transition, and its chromatic number can be arbitrarily high. And this is a construction using like a Knaser graph, so sort of topological construction. So for locally bipartite graphs, I have like a load of structural results, but this is sort of a praise to sort of the highlights. So you've got some n-vertex locally bipartite graph, and we know this thing doesn't have a K4 in it, so certainly its minimum degree is most 2/3, and you can drop down from there. And up down to 4/7, it remains 3 colourable. And this is tight because of that complement of the 7th cycle I showed earlier. At 4/7, that appears, and that's a 4 regular graph for 7 vertices. So suddenly you're no longer 3 colourable, but maybe you're 4 colourable. In fact, you are. So if you keep dropping down, you might be 3 colourable, but you definitely are homomorphic to a complement of the 7th cycle. So you have a lot of structure. You can keep going. Right down to sort of 6/11, you're at least 4 colourable. So we've got to get a table like this, and we can, you know, we don't know if 6/11 is tight. I think we should be able to lower it. And so there's a big, and we know that below 1/2, the chromatic number can be arbitrarily large. So this is a sort of another topological construction of MoCCA'20. So what happens between? Is there another threshold? So for triangle-free, there was a 2, 3, 4, and then we had a infinity. You know, is there sort of, are there 5 chromatic locally bipartite graphs in here, or are there infinitely many thresholds, or maybe there are no more thresholds? It's not kind of clear. I mean, it was pretty amazing that for triangle-free graphs, there are only 3 thresholds. I mean, people have conjectured. Like before, it was proven there was conjectures both ways. Cool, and I guess similar questions are sort of what are the way it was proven that all triangle-free graphs with minimum degree bigger than a third are 4 colourable was by coming up with an infinite sequence of graphs and saying that any triangle-free graph of that minimum degree must be homomorphic to one of them, and each of them happen to be 4 colourable. So we sort of need to understand the structure of these locally bipartite graphs. So finally, you've got some results on some more general locally bipartite, so locally tripartite, four-partite, and so on. And the definition is what you think it should be. So here again, you see this seventh, which is the same, like the gaps are the same seventh gap everywhere. And here, though, we know of even fewer thresholds. So it's not that we know less, I guess. It's just that in this first 6/7 bit, there are just fewer thresholds for locally tripartite and so on. So in everything above this 1 minus 1 over b plus 7 is b plus 1 colourable, and we know a construction using Schreier graphs at 1 minus 1 over b, which shows that below there it's arbitrary large compressing number. What happens in between? Are there more thresholds, or are there even fewer thresholds than for the locally bipartite case? Yeah, I think that's what to say. So I just finished with some sort of open problems. So, like, firstly, try and close the minimum degree stability gap. That'd be a nice problem to close. Also, what about, so minimum degree stability was what minimum degree guarantees close to R-partite? What about what minimum degree guarantees being close to R plus 1 partite or R plus 2 partite? Or yeah, something higher. And for sort of locally bipartite graphs, what comes after the complement of the 7th cycle? I've written this H2 plus because that was another graph that you saw earlier. That was is the next graph after the complement of the 7th cycle. What is the infinite sequence of graphs? Are any of them 5 chromatic? So is there another threshold, or are there fewer thresholds than the Trianglefree case? And for sort of more generally for locally bipartite, is there one threshold, or are there more? So a really simple one is: are any 5 chromatic graphs? Do any 5 chromatic graphs have minimum degree more than 2/3? So what's sort of tantalizing here is that for Trianglefree, we saw the 5 cycles, the interesting thing, and the 5 cycle is the complement of the 5 cycle. For locally bipartite graphs, the complement of the 7 cycle is the first interesting thing. So you'd think surely the complement of the 9 cycle should be the first interesting thing for locally tripartite, and it is locally tripartite, and it is 5 chromatic. But sadly, 2/3 is the point at which the chromatic number suddenly get arbitrarily large. So it doesn't. The complement of the 9 cycle isn't in the interesting range where the chromatic number is bounded. Great, yeah, I think that's everything I had to say.
Thank you very much. So shall we start by unmuting to thank Freddie? Does anyone have any questions?
That was a very nice talk. I think it was very clear, but yeah, it's interesting how these gaps, you don't know these thresholds there. What do you think is, I guess, the most?
Yeah, it's tricky. So in the Trianglefree case, just to give you like how wrong people guess things. So the paper that started off Trianglefree stuff was Erdős and Szymonovich in the 70s. They guessed bigger than 1/3 implies 3 colourable. So they totally missed that there were some 4 colourable things. And it took 10 years for Hateless to find an example. Yeah. And then Jin guessed there were infinitely many thresholds later, and that was telling wrong as well. So I don't know. I spent a while looking for 5 chromatic locally bipartite graphs, but not. I mean, I haven't got an efficient way for a computer to search these things, so it's not like I have a particularly good guess on them. I think possibly the most intriguing one is this one. I think there might not even be a threshold here. I think it might be the case that either you're b plus 1 colourable, if you're above 1 minus 1 over b, or you're infinitely below. This one, I'm more confident of that, but not that confident. And for like what graphs come next, so we've got these sort of a couple of graphs. What makes this things harder than the Trianglefree case, I think, for Trianglefree, these graphs we had here, they're all nested. As in, you may not see how how should I explain how you come up with them? You take a cycle of length 3k plus 2, and you join vertices to the ones next to them and the ones 4 away and 1 7 away. So this has got 5 vertices, 8 vertices, 11 vertices, and that would be sort of 4 regular with 11 vertices. So they're all nested, they're all homomorphic, and that's quite nice. But even like these first 2 graphs aren't nested. Neither contains the other, neither is homomorphic to the other. So I do know of an infinite family of locally bipartite graphs which are nested, which contain the complement of the 7 cycle. So if you sort of generalize the triangle-free version, those triangle-free graphs in the right way. But this H2 plus is like totally different. And also H2 plus, what's also interesting is it's not even regular. As in it's best, if you take the like right blow up, it's not actually regular. So this is an extreme example where some proportion of vertices have higher degree than everything else.
Can you go back to the picture of it? I think you had one earlier on the slides, right?
Yeah, so this isn't right. You need to blow this up slightly to get the minimum degree right. But this central lot of vertices, so this whole thing, when you blow it up properly, has 9 vertices, and all vertices have degree 5, except for the central vertex, which has degree 6. So this is an extreme example where some vertices actually genuinely have like a much larger degree than others.
Yeah.
So
and this list, how did you find it? Because you were saying a little bit about how you wanted their neighborhood to be locally bipartite, but when you were sort of doing this research, how can you tell?
Okay, yeah.
How did this story come about for you?
So yeah, I was thinking about this problem. So I was thinking about minimum degree stability, and then I worked out I need to think about locally bipartite graphs. So I put that to one side and spent a lot of time thinking about locally bipartite graphs in the first lockdown. So that was fun. And so what I was trying to do was say, let's take locally bipartite graphs with large minimum degree. What conditions do you need? What conditions imply they're 3 colorable? So down to 4/7, that's fine. You show they're 3 colorable, and then below 4/7, this thing appears, and it was sort of working out like if I add what little extra condition can I add which makes them 3 colorable, and it turns out you just need to forbid a certain sort of subgraph of this, and then so from there that's how you came up with a lot of these ones, was that these were the examples which contained this bad subgraph which made it 4 colorable. I guess T0 looks like particularly weird. That's a product of the proof of. I can't quickly explain this. So, if you imagine you've got a locally bipartite graph with large minimum degree, and you want to show it's 3 colorable, the proof, or like my proof strategy was, assume it's edge maximal. So if I add any edge, it's not locally bipartite. So if you add any edge, you create a odd wheel or like a K4. And so we think about missing edges. So it's kind of not too hard to show that the missing edge can't be from a center of an odd wheel to the exterior of an odd wheel, a sort of an edge counting argument similar to the one we did earlier with C. If the minimum degree was high enough, but when the minimum degree got too low, suddenly its edge counting argument broke. And so this sort of weird T0 thing, if you sort of stare at it, it's a 7 cycle with like these vertices are joined to 6 of the 7. So the missing edge is like vertex to, there's like a missing edge there, a missing edge there. Like these came about from like these sort of proof strategies. There wasn't like a nice. It was just like how the proof. Yeah, it was just like keep trying to drop the minimum degree and see like what broke in the arguments and what graphs came out of that. It's essentially what happened.
So yeah, I guess for larger values, it will get much more tricky to get the list of the graphs as well.
Yeah, I mean, it could be amazing, and maybe there are. You know, it's possible. There's not like a, because for triangle-free graphs, if you're above a third, if you know 0.34, there are only finitely many triangle like free graphs in this list above that minimum degree, and Like you would think that's true here, but maybe actually you can find sort of infinitely many locally bipartite graphs, none of which are homomorphic to each other, and have this like large minimum degree.
Do you have any other questions? Maybe I could ask one actually. Could you do some of this analysis? So instead of minimum degree, it feels like you could do something very similar with average degree, or maybe a different property there. You've talked about number of edges and minimum here.
So the danger with average degree again is this like this bad graph thing where you can create really high, like you can be far from being 100 partite,
right.
But then far from it is just some graph on a small proportion of vertices.
Yep, that's true.
I think there definitely would be, there are some graph properties that you could do where would like rule out this sort of thing.
Maybe like maximum average degree of degeneracy kind of stuff.
Yeah.
Thank you. Okay, maybe let's thank Freddie again.